In this video, we're going to continue our discussion of hypothesis testing, and we're going to introduce the concept of the comparing two sample means. So comparing the two means from different samples. So we'll just generally recall that our standard deviation of y bar is equal to sigma. That is our standard deviation of our population divided by the square root of n. When we don't know the standard deviation of our population, we should know the standard deviation of our sample. So in that case, we'll say the standard error of y bar is equal to S. That's the standard deviation of our sample divided by the square root of n. That's not new. You've been doing that before. Now, when we're comparing the means of two samples, we'll have two different samples. We'll have the mean of y bar 1 and we'll have the mean of y bar 2. So sample 1 and sample 2. Now, as we've done before, when we looked at adding and subtracting random variables from each other, we know that the equation of the expected value of x plus or minus y is equal to the expected value of x plus the expected value of y. Well, that's exactly what we're doing in this scenario, is we are doing the expected value of y bar 1 minus y bar 2, so that's the mean of sample 1 minus the mean of sample 2, is equal to the expected value of y bar 1 minus the expected value of y bar 2. So this is something that we've certainly done before, and if you need a refresher, you can go back to previous videos on adding and subtracting random variables from each other. So once we've established what expected value of y bar 1 minus y bar 2 equals, we need to recalculate our standard deviation. So our standard deviation of y bar 1 is equal to y bar 1 minus y bar 2 is equal to the square root of the variance of y bar 1 plus the variance of y bar 2. No different than in previous examples or in previous videos, the standard deviation of x plus or minus y is equal to the square root of the variance of x plus the variance of y. All right? Exactly what we've done in previous videos. Now, when we're working with our samples, we have our standard deviation of y bar 1 minus y bar 2 is equal to the square root of the standard deviation, sigma 1, the standard deviation of our population 1, divided by the square root of n1, that's the sample size of our first sample, all squared to get our to get our variance, right? Remembering that our standard deviation is equal to sigma divided by the square root of n. Therefore, our variance is equal to our standard deviation squared. So that's exactly what we're doing here. So this would be equal to sigma squared divided by the square root of n squared. Or we can simplify this, put this in brackets. And that's exactly what we have happening right here, plus sigma 2, that's the standard deviation of our population for sample 2, divided by the square root, this should say not n1, this should say n2, squared, and that is our standard deviation. Now, we can simplify this. So you can see that when we had the square root of sigma 1 divided by root n squared plus sigma 2 divided by root n 2 squared. What this then simplifies to is the square root of sigma 1 squared divided by n plus sigma 2 squared divided by n2, right? Why is that? Well, the square root of n1 squared is simply going to equal n. Now, when we don't know the standard deviation of our population, we're then going to divert to the standard error. So standard error of y bar 1 minus y bar 2 is equal to the standard deviation of our sample 1 squared divided by the sample size of our first sample plus the standard deviation of sample 2 squared divided by the sample size of our second sample. So once we've calculated our standard error, we can then revise our T-statistic. So our T-statistic is equal to the observed difference minus the expected difference or the true difference divided by our standard error. So this is very similar to what we've done before. You can think of this as the observed. The observed will just abbreviate to delta minus the expected delta or the true delta, the true difference, divided by our standard error of y bar 1 minus y bar 2. And that's, of course, as we calculate in this equation right here. Now, finally, when we're doing significance testing with t-scores, we need to remember that we need degrees of freedom. Now, when we're calculating degrees of freedom with two samples, we need to calculate our degrees of freedom, and it has its own special equation. So in our numerator, we have the standard deviation of sample 1 squared plus the standard deviation of our sample 2 squared divided by the sample size. All that sum is then squared divided by 1 over n1 minus n1. This should say n1, not n2. The standard deviation of sample 1 squared divided by n1 plus the 1 over n2 minus 1 times the standard deviation of our second sample squared divided by n2 all squared. This will make sense in a few minutes once we do a practice problem with it, but for now, let's just go to our problem. So here's our problem. So a market analyst wants to know if the new website he designed is showing increased page views per visit. A customer is randomly sent to one of two different websites which offers the same products but with different designs. He takes a random sample of customers, two from each website, and records their page views. And then here is the data. So in website 1, we have a sample size of 35. We have a mean of 7.7 and a standard deviation of 4.6. In our second sample, or our website 2, we have 42 observations, and mean of 7.3 and a standard deviation of 4.3. So we have 4 different questions here, but let's just go through them. So A, we're asked to find the estimated mean difference in page visits between the two websites. So what we're saying here is that the expected value of y bar 1 minus y bar 2 is equal to the expected value of y bar 1 minus the expected value of y bar 2. Whoops. Y bar 2. So this is equal to 7.7 minus 7.3, which is then equal to 0.4, right? 7.7 being our mean, our y bar 1, 7.7 y bar 1, 7.3 y bar 2, 7.7 minus 7.3 is 0.4. And of course, if we want, we can put our units here. We know that this is in pages. We're then asked in B, so we've done 1. In B, we're asked to calculate the standard error of the estimated mean difference. So the standard error of y bar 1 minus y bar 2 is equal to the square root of S1 squared divided by our sample size plus our standard deviation of our second sample divided by our second sample size. So we have a standard deviation of 4.6 and 4.3, and 35 and 42 is our sample size respectively. So 4.6 squared divided by 35 plus 4.3 squared divided by 42. So 4.6 squared divided by 35 gives us 0.60457 plus 4.3 squared divided by 42 gives us 0.440238. So 0.60457 plus 0.440238 gives us the square root of 1.044808, which gives us then a standard error of 1.02216. We'll just keep it at 5 decimal points there. So this is our standard error of y bar 1 minus y bar 2. Okay, great. So we've done B now. Calculate the T-statistic for the observed difference in mean page visits, assuming the true mean difference is 0. Okay, so C. So we're calculating a T-statistic. Well, this is going to be y bar 1 minus y bar 2 minus mu 1 minus mu 2 divided by the standard error of y bar 1 minus y bar 2. So y bar 1 is 7.7, y bar 2 is 7.4, and we're told in our question that we're to assume that the mean difference, the true mean difference, is 0. So we're going to say minus 0 divided by our standard error that we just calculated here in B to be 1.02216. So this gives us then 0.4 divided by 1.02216. So 0.4 divided by 1.02216, which gives us a t-score of 0.39. Now we can go to 4 decimal points, why not? 0.3913. Now the question is how many degrees of freedom? Because if we were to go to our t-chart, so if we were to go to our t-chart, we need to be able to look up how many degrees of freedom to find our critical value. So we can just erase some of these previous markings here. We don't need those. So let's go ahead and calculate how many degrees of freedom we have. So D, let's calculate our degrees of freedom. So this equation is a little bit long, as I'm sure you remember. So the equation is the following. So S1 divided by N1, S1 squared plus S2 squared divided by N2. This sum is squared divided by 1 over N1 minus 1 times S1 squared divided by N1 all squared plus 1 over N2 minus 1 times S2 squared divided by N2 all squared. So we can go ahead and just start plugging our values in. So let's go ahead. In our S1, our standard deviation of our sample 1 was 4.6. So we get 4.6 squared divided by our sample size, which was 35, right? Plus 4.3, our standard deviation of our second sample, divided by our sample size, which was 42. Importantly, this was squared. Divided by 1 over n minus n1, which is 35 minus 1, times our standard deviation of our first sample, which is 4.6 squared divided by 35. This is all squared, plus 1 over n2 minus 1, so 42 minus 1, times 4.3, the standard deviation of our second sample, 4.3 squared divided by 42. All of that was squared. So let's go ahead and punch some of this into our calculator. We're going to do this in kind of combined steps. So 4.6 squared divided by 35. We'll store that value in our calculator. And 4.3 squared divided by 42. Store that value in our calculator. So alpha A plus alpha B squared gives us a value here of 1.091627 divided by 1 divided by 34, 1 over 34, times 4.6 squared divided by 35 squared gives us 0.01075 plus 1 divided by 41 times 4.3 squared divided by 42, all squared, plus 0.004727. So 0.01075 plus 0.004727. So this then becomes equals 1.091627 divided by 0.015477. So 1.091627 divided by 1.091627 divided by 0.015477 gives us a degrees of freedom of 70. So we have 70 degrees of freedom on our t-test. So we remember that if we're going to look at, well, significance of 0.05, we want 0.025 in each tail. So what we're looking for is we're looking for our T critical here. So at 70 degrees of freedom. So we don't have 70 degrees of freedom, but let's first look up our confidence level here. So 0.025 in each tail for a cumulative total of 0.05, or otherwise our 95% confidence level. We don't have 70, so let's round down and let's use 60 as just a rough estimate. And what we're looking for is a T critical here of 2.00. So our T star here is 2.00. And what do we notice about our T score? Well, our T score that we calculated here in C was 0.3913. So the T that we calculated was 0.3913. So Therefore, the probability that t is greater than 0.3919 is greater than the probability that t is greater than 2.00. Therefore, in this case, if we had set hypotheses, which we didn't, but we would fail to reject the null hypothesis. So since we're here, we can set our hypotheses. So typically you do this prior to, but in this case we'll just say it's the same. So our null hypothesis would be that mu1 is equal to mu2. Our alternative hypothesis is that there would be a difference. So mu2 does not equal mu1. In this case, because our probability is greater than 0.05, in other words, the area to the right of this t critical, or our t calculated, is greater than our t critical that we highlighted right here. To this end, we would fail to reject the null hypothesis. That's it for this video, but if you found that it helped make statistics easy, consider showing your support by giving the video a like. And if you still need more help with statistics, then consider subscribing to the channel if you haven't already. I look forward to solving many more problems with you next time.